The version of you that dies tonight already exists in another timeline. What if every choice you make doesn't just change your future, but splits reality? In some interpretations of modern physics, every possible outcome may already be unfolding in parallel versions of reality. That means somewhere in the multiverse, there could be a version of you living a completely different life, or even reaching a different ending. Today, we're exploring the science behind parallel timelines and why this idea is both fascinating and unsettling. The version of you that dies tonight already exists in another timeline. A person steps off the curb on a busy street and walks forward without thinking too much about what is happening around them, while cars move past at high speed and the world continues like it always does, steady and normal. But in a deeper way that is not visible to the eyes, something far more unusual may already be unfolding at the same exact moment. In one version of what happens next, a driver notices the person just in time, slows down, and the moment passes without incident, and life continues without interruption, as if nothing special ever happened at all. The person reaches the other side of the road, maybe checks their phone, maybe adjusts their pace, and keeps going forward into their day, without ever knowing that something very small almost went differently. But in another version, happening at the same exact moment according to one interpretation of modern physics, the timing is slightly off. The distance is slightly wrong, and the outcome becomes irreversible in that version of events, where the car does not stop in time, and the story of that version of the person ends right there, in a way that no one in that version can undo or reverse. Both of these outcomes come from the same starting moment, the same street, the same movement, the same decision to step forward, and yet they end in completely different results that cannot both be experienced from a single point of view, even though they seem to be generated from the same physical situation. According to one interpretation of quantum physics, these two outcomes are not just possibilities that are imagined in theory, but instead, they may both exist as real outcomes that happen at the same time in different branches of reality, even if each version of the event only experiences one result and never sees the other. This idea is how some interpretations of quantum mechanics describe the structure of reality, where instead of one single outcome being chosen when something happens, every possible outcome continues forward, each in its own separate path that does not interact with the others again after the moment of change. If this interpretation is correct, then the world is not a single continuous line of events that everyone shares, but instead something that may constantly divide into multiple directions every time something uncertain happens at a very small physical level. If reality really works this way, then it means there could be multiple versions of the same person existing at the same time, each one living through slightly different outcomes that come from the same starting point, even though none of those versions would ever be aware of the others once the split has happened. This leads to a deeper question, because if multiple versions of a person can exist after every uncertain event, then it becomes necessary to ask what happens when one of those versions continues living and another version does not, especially in situations where outcomes are extreme and final in nature. The question becomes even more direct when it is applied to a single night, a single moment, or a single decision. Because if reality truly splits at the smallest level of uncertainty, then there could be versions of a person who survive events that other versions do not, all existing as part of the same underlying physical process that governs everything in the universe. So the question is not only whether reality can split, but whether those splits are happening constantly right now in ways that no one can directly see or measure from the inside of their own experience. Could reality be dividing all the time, not just in rare moments, but continuously, as every small interaction between particles creates new branches of possible outcomes that all move forward without ever crossing paths again? Could multiple versions of you already exist at this very moment, each one following a slightly different version of your life, shaped by tiny changes that happened in the past that you never noticed at the time they occurred? And if that is the case, then one of the most unsettling ideas that follows from it is the possibility that every moment you experience could also be happening in other versions where the outcome is not the same, including versions where the final result is very different from the one you are currently living through. If that is true, then the idea that one version of you dies tonight is whether there exists a version of events where that outcome naturally happens as part of a physical process that produces all possible results. When most people hear the word timeline, they do not think about physics. They think about movies, science fiction shows, strange internet stories, or dramatic scenes where someone changes the past, wakes up in a different present, or suddenly remembers a world that no one else seems to know. In popular culture, a timeline is often shown as a clean line of events that can be broken, edited, replaced, or merged with another version. A person presses a button, travels through time, changes one moment, and history becomes something else overnight. It is exciting, dramatic, and easy to understand. But it is also very different from what scientists usually mean when they talk about time, events, and the structure of reality. This matters because words shape how people understand science. If someone hears that physics allows many timelines, they may imagine roads floating through space, each carrying different versions of history, with people moving between them like changing lanes on a highway. That picture is powerful, but it is not how mainstream science describes the universe. Scientists use more careful language, and when they discuss things that sound like timelines, they usually mean something far more technical, mathematical, and less cinematic. So before asking whether another version of you exists somewhere else, or whether one version of you dies while another survives, what does the word timeline actually mean in science? In modern physics, especially after the work of Albert Einstein, time is not treated as a separate ticking clock floating outside the universe. Time is woven together with space into one structure called space-time. This means the universe is often described not as a three-dimensional place where time passes from outside, but as a four-dimensional system where location and time are connected. To understand this, imagine giving someone an address. You normally need 3 pieces of information to locate something in space. You need where it is left or right, forward or backward, up or down. That gives 3 dimensions. But if you want to describe an event, like a lightning strike or a person stepping into a road, location alone is not enough. You also need to know when it happened. Once you add time, you now have 4 coordinates that describe an event in space-time. That means your birth, your first day at school, the moment you dropped your phone last week, and the moment you started watching this documentary can all be described as events placed somewhere in this 4-dimensional structure. In this scientific sense, a timeline can mean the ordered sequence of events associated with an object or a person moving through space-time. Your life, in this framework, can be imagined as a path through space-time. Physicists call this a world line. It is not a glowing line you can see. It is a way of describing where you are at different moments. Every second you live adds another point to that path. A car has a world line. A planet has a world line. A beam of light has a special kind of path through space-time. This is one serious scientific meaning behind what people casually call a timeline. Notice what this does not mean. It does not mean there are many cinematic copies of history stacked beside each other. It does not mean you can step out of one line and into another. It means that events happen in an ordered way and can be mapped using the geometry of space-time. Einstein's theories also changed how we think about past, present, and future. In daily life, it feels like the present is universal, like everyone shares one exact now. But relativity showed that the timing of events depends on motion and gravity. 2 observers moving differently may disagree about which distant events are happening now. That does not mean reality is fake. It means time is more flexible than human intuition suggests. So in one scientific sense, timeline simply means a path of events through space-time. It is real, useful, and based on tested physics. But it is not the dramatic version shown in fiction. The second meaning of timeline appears in models that describe diverging histories. This is where things start to resemble the language people use online, but the scientific meaning is still more careful than the popular one. Scientists often use branching diagrams to study systems where multiple futures are possible. These are not alternate universes by default. They are tools used to understand how different outcomes can grow from the same starting point. Imagine weather forecasting. A storm begins over the ocean. Small changes in temperature, wind speed, moisture, or pressure can produce very different results several days later. One branch of the forecast brings heavy rain inland. Another keeps the storm offshore. Another weakens completely. Meteorologists run many models because the future depends on sensitive details. This kind of branching is common in science. Economists model markets with multiple possible paths. Engineers model system failures with branching outcomes. Biologists model population changes with different conditions. Computer scientists use decision trees. In each case, one starting state can lead to many possible later states, depending on conditions and interactions. This is sometimes described casually as different timelines. But what scientists really mean is different possible histories of the same system. Chaos theory gives another strong example. In chaotic systems, tiny changes in the beginning can create large differences later. This is often simplified as the butterfly effect. A small shift early on can completely reshape what happens later, not because magic occurred, but because the system is sensitive to initial conditions. Think of two balls released almost side by side at the top of a rough hill. At first, their motion looks nearly identical, but small differences grow over time until one rolls left and the other right. After enough time, their paths become completely different. Same starting region, different histories. Again, these are sometimes called timelines in casual language, but in science they are modelled outcomes. They are branches in prediction space, not confirmed parallel worlds. Then we arrive at the version most connected to your documentary topic, quantum branching interpretations. Quantum mechanics describes particles using mathematical states that can include multiple possibilities before measurement. Different interpretations try to explain what this means. One interpretation suggests that instead of one outcome being chosen and the rest disappearing, all outcomes continue in separate branches. This is where people often jump to the word timeline. They imagine fully formed universes splitting every second like branches of a tree. That image is dramatic, but the actual physics language is more precise. The theory concerns the evolution of quantum states and how different outcomes become effectively separate due to a process called decoherence. In simple terms, tiny quantum possibilities can become separated so strongly that they no longer interfere with each other in ordinary experience. Each branch contains observers who experience one consistent result. They do not feel themselves splitting. They simply experience a normal world. So yes, branching possibilities do exist mathematically in some interpretations of quantum theory, but that is not the same thing as proving countless cinematic timelines in the popular sense. The third scientific meaning behind timeline language involves parallel solutions to equations. In physics, equations often allow more than one possible outcome from the same starting setup, especially when probability is involved. If you toss a coin, there are two obvious outcomes. If you simulate gas molecules, there are huge numbers of possible arrangements. If you model radioactive decay, you may know the odds, but not the exact moment a specific atom will decay. The equations describe a space of possible futures. Some are more likely than others. Some may be nearly impossible. But the math can contain many allowed results. This is important because people sometimes confuse possibility with reality. Just because equations allow many outcomes does not mean all of them physically occur in separate worlds. That depends on interpretation and evidence. Physics often gives predictions without settling every deep philosophical picture behind them. That is why scientists are careful. They distinguish between what the equations calculate, what experiments measure, and what story we tell about why those measurements happen. So when someone says there are many timelines, the first question should be, do you mean many modelled futures, many branches in a quantum interpretation, or many fictional universes that characters jump between? These are not the same claim. Now we need to address something clearly. There is no mainstream evidence that timelines collide with each other. There is no accepted evidence of people waking up in another universe because they made a different choice. There is no confirmed case of two histories merging, memories leaking between worlds, or travellers moving from one branch of reality to another. What does exist are mathematical structures where branching possibilities are real parts of the model. Scientists use these tools constantly. They matter deeply in forecasting, probability, computation, and some interpretations of quantum mechanics. The physics problem that broke reality. At the start of the 20th century, science believed it was close to finishing the story of nature. For centuries, physics had grown stronger with each generation. The motion of planets could be calculated. Falling objects could be predicted. Machines could be built with confidence. Heat, sound, pressure, motion, and electricity were becoming understandable through clear laws. Many scientists thought the hardest work had already been done and that only small details remained. That confidence came from classical physics, the older system built through the work of Isaac Newton, James Clerk Maxwell, and many others. Classical physics described a world that behaved in ways people could imagine. If you knew the position of an object and how fast it was moving, you could predict where it would go next. Causes led to effects in a steady chain. The universe looked like a giant machine that followed rules with perfect order. Then scientists looked deeper. As instruments improved, they began studying matter at smaller scales. They wanted to understand atoms, light, and the hidden structure of substances. But the more closely they looked, the more the old rules began to fail. The same physics that could explain cannonballs and planets struggled badly when applied to tiny particles. Nature stopped behaving like a neat machine and started behaving like something far stranger. One of the first major cracks appeared in the study of heat and light. When hot objects glow, they release energy as radiation. Scientists tried to predict this glow using classical equations. The results were disastrous. The math said hot objects should release infinite energy at certain frequencies, which clearly did not happen in real life. The theory produced nonsense. A German physicist named Max Planck tried to solve the problem in 1900. He made a move so unusual that even he first treated it as a mathematical trick. He proposed that energy was not exchanged smoothly in any amount whatsoever. Instead, it came in tiny packets, small fixed units later called quanta. Energy, which people assumed flowed continuously, seemed to come in steps. This idea was revolutionary because it attacked a deep assumption about nature. If Planck was right, then reality at small scales was not perfectly smooth. It was granular in some way. Energy could jump from one level to another rather than slide endlessly through all possible values. What began as an attempt to fix one problem opened the door to a new kind of physics. Then came Albert Einstein. In 1905, while studying light and a strange effect where metals release electrons when exposed to certain light, he pushed the idea further. He suggested that light itself could behave as if it came in packets of energy. These packets later became known as photons. This was shocking because light had long been understood as a wave. Waves spread out, waves interfere, waves bend and overlap. Water waves and sound waves were familiar examples. Light also showed wave behavior in experiments. Yet Einstein's explanation required light to sometimes act like a particle delivering energy in chunks. So which was it, wave or particle? The answer seemed to be both, depending on how it was tested. This was the first sign that the universe at tiny scales would not respect everyday categories. Things could behave in one way in one experiment and another way in a different experiment. The old demand that objects must fit clean labels began to collapse. Then scientists turned to the atom itself. Atoms had been imagined as the basic units of matter, but their internal structure was unknown. J.J. Thomson discovered the electron, proving atoms were divisible. Ernest Rutherford later showed that atoms contain a tiny dense nucleus. But this created a new problem. If electrons orbited the nucleus like planets around the Sun, classical physics said they should radiate energy continuously, spiral inward, and crash into the nucleus very quickly. Atoms should be unstable. But atoms clearly existed. Niels Bohr proposed a bold solution in 1913. He suggested that electrons could occupy only certain allowed orbits or energy levels. They did not move in any path they wanted. They could jump between levels by absorbing or releasing fixed amounts of energy. Again, the universe seemed quantized. Not smooth motion, but allowed states. Not any value, but selected levels. Bohr's model was not the final answer, but it explained why atoms emit specific colors of light and why matter is stable. It was another sign that small-scale reality obeyed rules unlike anything visible in ordinary life. Then the deeper revolution arrived. Scientists including Werner Heisenberg, Erwin Schrödinger, Paul Dirac, and others developed quantum mechanics in the 1920s. This was not one single idea, but a full mathematical framework for describing particles, atoms, and microscopic systems. It worked extraordinarily well. It predicted experimental results with stunning accuracy. Electronics, chemistry, lasers, semiconductors, and modern technology would later depend on it. But while the equations worked, their meaning was deeply unsettling. One key discovery was quantized energy. Particles in atoms do not carry just any energy they please. They occupy allowed levels. Jumping between levels releases or absorbs exact amounts. This explained why atoms emit precise lines of color rather than random smears. Another discovery was the uncertainty principle, developed by Heisenberg. This principle did not mean scientists were clumsy or instruments were poor. It meant nature itself places limits on what can be known simultaneously. The more precisely you know a particle's position, the less precisely you can know its momentum, and vice versa. This was not a practical inconvenience. It was built into reality as described by quantum mechanics. In classical physics, an object has a position and speed whether or not you measure them. In quantum physics, certain pairs of properties cannot both be sharply defined at the same time in the usual sense. The universe was no longer a machine with hidden exact numbers waiting to be revealed. Then came superposition. This is one of the strangest ideas in all of science. A quantum system can exist in multiple possible states before measurement. Not because we are ignorant in the normal sense, but because the mathematics describes a combination of possibilities. An electron can be in one location and another possible location within the allowed description. A system can carry multiple potential outcomes together until interaction forces a measurable result. A particle can be in a state linked to more than one possibility at once. To describe this, scientists use the wave function. The wave function is a mathematical object containing information about the possible outcomes of a system. It does not give a simple single answer, like a classical object's exact path. Instead, it gives probabilities for what may be found when measured. This means quantum mechanics often predicts not certainty, but chances. If you repeat the same setup many times, you may get patterns with precise probabilities, even though each single event appears unpredictable. The laws are exact, but what they govern is probability. That alone was enough to disturb many scientists. Einstein famously disliked the idea that chance seemed fundamental. He believed deeper hidden order should exist. Yet experiment after experiment supported the quantum framework. Then came the weirdest fact of all. Particles often do not appear to choose a definite state until measurement. Consider electron spin. Spin is a quantum property that can be measured in different directions. If measured along one axis, an electron may be found spin up or spin down. Before measurement, Quantum theory can describe the electron as a combination of both possibilities relative to that measurement setup. When the measurement happens, only one result appears. Where did the other possibility go? Now consider the double-slit experiment. Fire photons or electrons toward a barrier with two openings and detect where they land. If no one measures which slit each particle passes through, the pattern on the screen shows interference, a wave-like result suggesting each particle behaves as if multiple paths matter. But if you measure which slit it goes through, the interference pattern disappears and particle-like behavior emerges. The act of obtaining path information changes the outcome. This is one of the most famous experiments in physics because it seems to say reality depends on what is measured. More carefully stated, the setup of measurement affects what kind of result emerges. Then there is radioactive decay. A single unstable atom may decay now, later, or much later. Quantum theory can predict the probability over time for many atoms, but not the exact moment a specific atom must decay. Before detection, the future outcome is treated probabilistically, yes or no, decayed or not yet decayed. These examples reveal a deep divide between the tiny world and the everyday world. At normal human scales, objects seem definite. A chair is here, not spread across possibilities. A ball has one path through the air. A traffic light is red or green, not both in practical experience. But at tiny scales, particles behave unlike normal objects. They can exist in superposition. They can carry multiple possible states before measurement. Outcomes appear probabilistic rather than deterministic in the classical sense. An electron may be described as having probability to be found here or there. Its spin may be unresolved relative to a chosen measurement until interaction occurs. The mathematics evolve smoothly, but the observed result comes as one definite answer. This creates the central puzzle. If the equations describe many possibilities, why do we experience one outcome? When measurement occurs, what exactly counts as a measurement? Is it a detector, a human observer, any interaction with the environment? Does the wave function physically collapse into one result, or is collapse only a useful update in knowledge? Different answers lead to different interpretations of quantum mechanics. This became known as the measurement problem. The measurement problem is not about whether quantum theory works. It works extremely well. It is about what the theory says reality is doing between preparation and observation, and why observation yields one clear result from many allowed possibilities. Imagine a system described by multiple outcomes. The mathematics allows them together. Then a measurement returns one answer. If the equations governing the system evolve continuously, where does the sudden single result come from? Some interpretations say collapse is real. At measurement, the possibilities reduce to one actual outcome. Some interpretations say hidden variables determine results in ways not obvious from standard theory. Some interpretations say all outcomes continue, but observers become linked to only one branch. This is where the debate that sounds like timelines begins. If the universe does not simply choose one path in the ordinary sense until interaction, then what happens to the other possibilities present in the mathematics? Are they erased? Never real to begin with? Hidden from us? Still existing in some separated form? That question changed physics from a study of motion into a study of reality itself. Because once you ask where the unused outcomes go, you are no longer discussing only particles. You are discussing the nature of existence, observation, and why the world appears singular when the equations often describe plurality. The strange part is that this crisis did not come from failure. It came from success. Quantum mechanics became one of the most accurate scientific frameworks ever built. Its predictions were tested repeatedly and confirmed. The devices around modern life rely on it. Yet at its core, the meaning of its success remains debated. The old classical dream was simple. Reality has definite properties. Objects move on clear paths. If you know enough, you can predict everything. Quantum mechanics broke that picture. It replaced certainty with probability. smooth values with quanta, fixed paths with wave functions, and clear pre-existing states with measurement-dependent outcomes. It showed that nature at tiny scales does not resemble tiny billiard balls moving through empty space. And once that happened, a new question emerged that still has not fully gone away. If one observed world appears from many possible worlds in the mathematics, what selects it? That question would inspire some of the boldest ideas in science, including the possibility that nothing is selected at all. Schrödinger's cat and the measurement crisis. By the 1920s, quantum mechanics had become one of the most powerful scientific tools ever created. It could explain atoms, chemical behavior, radiation, and the strange actions of particles too small to see. Its equations worked with stunning accuracy. But even while the theory succeeded in laboratories, many of the greatest scientists alive were deeply uneasy about what it seemed to say. They could use the mathematics and trust the predictions, yet still disagree about what reality itself was doing underneath the numbers. One of the most troubled by this situation was Erwin Schrödinger, an Austrian physicist whose name would become permanently tied to one of the most famous thought experiments in science. Schrödinger was not an outsider mocking science. He was one of the architects of quantum theory itself. He developed wave mechanics, a major form of quantum mathematics, and introduced the wave equation that still carries his name. His work helped shape the modern understanding of electrons and atomic systems. But because he understood the theory so deeply, he also saw its most uncomfortable consequences more clearly than many others. He recognized that if the quantum rules were taken seriously and applied without limits, they seemed to lead to conclusions that clashed with ordinary experience in a dramatic way. At the heart of the problem was superposition, the idea that a system can be described as containing multiple possible states before measurement. For a particle, this might mean different positions or different spin values. In the microscopic world, this strange behavior had already become part of accepted physics. But Schrödinger wanted to expose a deeper issue. If these rules are true for tiny particles, where exactly do they stop? At what point does the blurry world of possibilities become the clear world of everyday objects? To make the problem impossible to ignore, he imagined a sealed box. Inside the box is a living cat. Also inside is a small amount of radioactive material, a detector, and a device containing poison. The setup is simple. If the radioactive atom decays, the detector registers it, triggers the mechanism, breaks the poison container, and the cat dies. If the atom does not decay, nothing happens, the poison remains sealed, and the cat stays alive. The fate of the cat depends entirely on the quantum behavior of one tiny atom. Now comes the disturbing part. According to the quantum rules, as they were often described, before the box is opened and the result is observed, the radioactive atom exists in a superposition of decayed and not decayed states. If the detector is linked directly to the atom, then the detector should also be in a mixed state of triggered and not triggered. If the poison device is linked to the detector, then it too should be both activated and not activated in the mathematical description. And if the cat is linked to the poison device, then the cat becomes part of that same chain. So before observation, the cat is mathematically alive and dead. Schrödinger did not create this example because he believed cats truly become half alive and half dead in any ordinary sense. He created it to show how absurd the measurement problem had become. If the equations are applied consistently, then a tiny uncertain event appears able to spread upward into larger and larger systems until an ordinary object, even a living animal, is trapped inside a quantum superposition. That conclusion felt ridiculous to many scientists, including Schrödinger himself. The experiment was meant to force a question that could no longer be avoided. If quantum laws apply to atoms, why should they not apply to detectors made of atoms? If they apply to detectors, why not poison devices? If they apply to those, why not cats? If cats are made of atoms, why should they be exempt? And if cats are not exempt, Then what about brains, people, laboratories, cities, planets, or entire worlds? This is where the crisis deepened. The problem was never really about cats. The cat was a mirror held up to the theory. It exposed the unclear boundary between the microscopic world, where superposition seemed accepted, and the macroscopic world, where things appear definite. Everyday life does not feel like a haze of overlapping outcomes. You do not experience your coffee as both hot and cold. You do not experience your front door as both open and closed in one moment. A car on the road is either there or not there in normal experience. Yet quantum theory, taken literally and universally, seemed to allow a more complicated picture. Some physicists responded by saying measurement causes collapse. When an observation happens, the many possibilities reduce to one real result. The atom becomes decayed or not decayed. The detector becomes triggered or not triggered. The cat becomes alive or dead. But this answer immediately raised another problem. What exactly counts as a measurement? Is it a machine detecting a signal? Is it a human seeing the result? Is it consciousness itself? Is it any interaction with the environment? Where is the line, and why does nature care about that line? No one could point to a clean, universally accepted boundary. If a Geiger counter clicks in an empty room with no person present, has measurement happened already, or only when someone later checks the machine? If a camera records the result, but no one watches the footage for hours, when did reality become definite? If a sleeping scientist is in the room while the detector runs, does the scientist's brain count? These questions were not jokes. They exposed how incomplete the interpretation of measurement seemed to be. The cat thought experiment made this confusion visible in one unforgettable image: a sealed box, a living creature, a quantum event, and a theory unable to clearly explain when possibility becomes fact. This matters because the issue is not limited to laboratory puzzles. It reaches into every event shaped by uncertainty. Replace the cat with human life, and the emotional force becomes immediate. A car crash is narrowly avoided, or it is fatal. A medical scan reveals a harmless growth, or a dangerous one. A plane lands safely, or it crashes. A person slips near stairs and recovers balance, or falls badly. In ordinary life, one outcome occurs, and the others do not. But if branching interpretations of quantum mechanics are correct, then all physically allowed outcomes may continue in separate branches, even though each observer experiences only one. That is why Schrödinger's cat still matters. It transforms an abstract problem into something personal. If one tiny uncertain event can spread into large consequences, then quantum measurement is not only about particles. It becomes about lives, histories, and the structure of reality itself. To understand why the thought experiment remains powerful, it helps to see what Schrödinger was criticizing. Many early explanations of quantum mechanics were practical. They told scientists how to calculate results, not necessarily what existed before measurement. This worked well in practice, but it frustrated those who wanted a clear picture of reality. Schrödinger feared that people were accepting a successful method while ignoring unresolved meaning. The cat forces meaning back into the room. Either the cat has a definite condition before the box is opened, or it does not. If it does, then perhaps the theory is incomplete and hidden details determine the result. If it does not, then somehow an everyday object is caught in a state unlike anything normal experience reveals. Both options are uncomfortable. Later developments in physics introduced the idea of decoherence, which explains how interaction with the environment rapidly destroys delicate quantum interference for large systems. In simple terms, a cat in a box is not isolated from the world the way a single particle can be in a controlled experiment. Air molecules, heat, internal biological processes, and countless interactions cause quantum coherence to spread into the environment almost instantly. This helps explain why large objects appear definite and why we do not see live-dead mixtures in daily life. But decoherence, while powerful, does not by itself fully settle the deepest question: It explains why branches stop interfering and why outcomes look classical, but it does not necessarily explain why one specific outcome is the one consciously experienced. The measurement crisis therefore changed form, but did not completely vanish. This is exactly where the door opens to many worlds. If collapse is hard to define, one radical option is to remove collapse entirely. Let the quantum equations always apply. Let the atom evolve into decayed and not decayed components. Let the detector become linked to both outcomes. Let the cat become alive in one branch and dead in another. Let the observer opening the box become linked to seeing a live cat in one branch and a dead cat in another. No special moment of collapse is required. The universe simply branches into separate histories that no longer interact. In that view, Schrödinger's cat is not absurd because the cat is both alive and dead in one experienced world. Instead, there are separate branches where each condition is definite. One observer sees the living cat, another sees the dead cat. Each version feels they encountered a single, clear result. Whether one accepts this interpretation or not, it shows why the cat experiment became historic. It forced physicists to confront the possibility that the measurement problem could not be solved with vague language forever. Either some mechanism chooses outcomes, or all outcomes continue, or the theory must be modified in some other way. The thought experiment also reveals something profound about scale. A tiny quantum event can be amplified into large consequences. One atom changes a detector. The detector changes a mechanism. The mechanism changes a life. This chain from microscopic uncertainty to macroscopic result is not fantasy. Modern technology depends on amplification of tiny signals all the time. Sensors detect minute events and convert them into visible effects. Schrödinger used that same logic to show that the small world and large world cannot be neatly separated by convenience. And once that barrier falls, everyday certainty becomes harder to take for granted. Your life feels like one continuous story because you remember one path. You crossed the street safely. The test came back clear. The plane landed. You caught yourself before falling. But quantum theory raised a dangerous possibility. Perhaps experience of one path does not prove only one path exists. That does not mean every imagined fantasy becomes real. Physics still follows laws, probabilities, and constraints. But it means the old idea that nature always travels one fixed road from start to finish may not be the only way to understand events. Schrödinger's cat survives because it speaks to everyone immediately. You do not need advanced mathematics to feel the tension. A hidden box contains uncertainty tied to life and death. Open it and reality seems forced to answer. Until then, the theory appears to hold both answers at once. Few scientific images have carried such power. It is simple enough for beginners, deep enough for experts, and sharp enough to expose unanswered questions almost a century later. The cat is not famous because it is cute or strange. It is famous because it revealed a crack running through the center of modern physics. The world of particles obeys rules unlike common sense, yet the world of people appears solid and singular. Schrödinger asked how those two worlds connect. No one has produced a final answer accepted by all. And once the cat is replaced by a person, once the sealed box becomes a hospital room, a highway, an aircraft cabin, or a staircase, the problem stops feeling distant. It becomes a question about whether reality selects one fate or carries more than one forward beyond what any single mind can witness. The man who refused collapse, Hugh Everett III. By the middle of the 20th century, quantum mechanics had become one of the most successful scientific theories ever built, yet it still carried a deep wound at its center. The equations described how systems changed over time with extraordinary accuracy. But when measurement entered the picture, many physicists accepted a strange extra step. Before observation, a system could be described through multiple possibilities. After observation, one result appeared. To explain that change, many interpretations spoke of collapse. The wave function, which had contained several possible outcomes, was said to reduce into one actual state. For many scientists, this was good enough. The theory predicted experiments correctly and practical work moved forward, but not everyone was satisfied. Some physicists believed collapse sounded less like a true explanation and more like a patch placed over a deeper mystery. Why should nature evolve smoothly according to equations most of the time, only to suddenly behave differently during measurement? What exactly counts as a measurement? Why should reality wait for observation to become definite? Into that unresolved problem stepped a young man named Hugh Everett III. Everett did not arrive as an established giant of physics. He was a graduate student at Princeton University. Brilliant, bold, and willing to challenge ideas that many older scientists treated as settled. He studied under John Wheeler, one of the most respected physicists of the era, a thinker known for curiosity, imagination, and interest in the foundations of reality. Wheeler encouraged difficult questions, and Everett had one of the most dangerous questions possible. What if collapse never happens at all? That proposal, published in 1957, would become one of the most controversial ideas in modern science. Everett suggested that the strange divide between smooth quantum evolution and sudden measurement collapse was unnecessary. The mathematics of quantum mechanics already described how systems evolve. Instead of adding a special rule for measurement, he argued that the equations should be trusted everywhere, at all times, with no exceptions. In Everett's view, the wave function never collapses. This sounds simple, but the consequences were enormous. If a quantum system contains multiple possible outcomes and nothing collapses those possibilities into one, then the outcomes do not disappear. They continue. Each possible result remains part of reality, carried forward in separate histories generated by the same underlying equations. In everyday language, one universe becomes many outcome histories. That phrase can easily be misunderstood, so it helps to slow down. Everett was not saying magical worlds pop into existence from nowhere, like scenes in a fantasy film. He was saying that if the quantum state contains several possible results and the equations evolve continuously without collapse, then those results become separate, non-interacting branches of the total physical description. Imagine a coin triggered by a truly quantum event. If the quantum event can lead to two outcomes, then in one branch the coin lands heads and in another it lands tails. Each result continues forward consistently. Observers linked to one branch experience heads. Observers linked to the other experience tails. Neither sees both. Now scale that idea upward. You accepted the job in one branch. You rejected it in another. You met someone in one branch. In another, you never crossed paths. You boarded the flight in one branch. In another, you missed it. You walked home safely tonight in one branch. In another, events turned differently. This is why Everett's theory became so provocative. It replaced the old image of randomness, choosing one path and destroying the rest. Instead, reality keeps every branch allowed by the quantum structure. That shift was radical because collapse had become part of how many people talked about quantum mechanics. It may have seemed mysterious, but it also kept the world singular. One measurement, one result, one experienced history. Everett removed that comfort. If all outcomes continue, then the single world of common sense may be only one branch inside something far larger. To understand how bold this was, remember the intellectual climate of the time. Many senior physicists focused on using quantum mechanics rather than rethinking its meaning. Foundational questions were often treated as distractions. The theory worked. Why reopen philosophical trouble? Everett did not accept that attitude. He believed the foundations mattered because they determined what kind of reality science was actually describing. If a theory succeeds so well, then its strange implications should be faced honestly, not hidden behind vague language. His doctoral work at Princeton developed what he called the relative state formulation. Later generations would popularize it as the many worlds interpretation. Everett's own language was more technical and less dramatic. He focused on how observers become correlated with outcomes. If a system has several possible results, then an observer measuring it becomes linked to each result in separate components of the total state. That means the observer is part of the quantum story, not outside it. This was another important break from older thinking. Traditional descriptions often treated the observer as if standing outside the system, stepping in at measurement. Everett instead placed observers inside the physical universe, governed by the same laws as everything else. When you measure a quantum event, the measuring device changes state. Your brain changes state. Memory forms. In Everett's picture, these changes occur in branching correlation structures, not by magical collapse. One version of you remembers seeing heads. Another remembers tails. Each version experiences one clean result and feels no awareness of the other. The idea was elegant in one sense. It removed the special status of measurement. There was no mysterious moment where nature switched rules. The same equations applied continuously from particles to detectors to people. But elegance came at a price. If every possible outcome continues, then reality may contain an immense number of branches. Every interaction that amplifies quantum uncertainty into larger consequences could produce further separation of histories. The total structure becomes unimaginably vast. Many physicists saw this as extravagant. Why multiply worlds when one observed world seems enough? Why accept a giant, invisible branching structure when no experiment obviously forces it? Others questioned what exactly counts as a split. Does branching happen at every microscopic interaction? Only when outcomes become irreversible. Only when decoherence separates possibilities strongly enough. If branching language is used, where precisely are the boundaries? Then came another hard problem: probability. If all outcomes happen, what does it mean to say one outcome has a 30% chance and another 70%? In normal thinking, probability measures uncertainty about which single result will occur. But if all results occur somewhere in the branching structure, why do probabilities still matter? And why do experiments match the usual quantum probabilities so precisely? Supporters of Everett developed sophisticated answers involving rational expectation, branch weights, and the mathematical structure of the wave function. Critics remained unconvinced. The debate continues. Yet even with these objections, some scientists took Everett seriously for strong reasons. First, his framework uses the standard quantum equations continuously. It does not insert a separate collapse rule that acts differently from ordinary evolution. Many physicists value theories that avoid special exceptions. Second, it treats observers as physical systems inside the universe, not mysterious external agents. This fits the scientific instinct that humans should not sit outside natural law. Third, later work on decoherence helped explain how branches could become effectively independent without requiring visible classical splits. As systems interact with environments, interference between alternatives becomes negligible, making each branch appear like a stable classical world from within. These developments gave Everett's once neglected idea new life. But in 1957, that future was not obvious. Everett's theory was largely ignored by mainstream physics. Some found it too strange. Some found it unnecessary. Others simply preferred to avoid interpretational battles. Wheeler himself supported Everett in some ways, but also softened aspects of the presentation to make it more acceptable to the scientific community. Even then, the reception remained cold. The young physicist who challenged collapse did not become the center of a great academic movement. He left academia early and moved into defense analysis and applied work. Instead of decades leading university departments and shaping generations of students, Everett stepped away from frontline academic physics. There is something striking about that history. The theory that may have created infinite versions of you was almost buried. Ideas sometimes survive not because they are immediately celebrated, but because they refuse to die. Everett's did exactly that. In the 1970s, physicist Bryce DeWitt became one of the most important figures in reviving and promoting the interpretation. DeWitt gave it the name many worlds, a label Everett himself did not originally use in that popular form. The name captured public imagination instantly. It also attracted criticism because it sounded more dramatic than the careful mathematics behind it. Still, the label stuck. Later, David Deutsch, a pioneering thinker in quantum computation, argued seriously for many worlds as the best explanation of quantum processes. Deutsch linked deep questions about reality to the power of quantum computing, helping bring Everett's ideas into modern discussions rather than leaving them as historical curiosities. In more recent years, physicist Sean Carroll has openly defended Everett-style interpretations as clean, natural readings of quantum mechanics. Carroll argues that the equations already tell a coherent story if we stop demanding collapse and accept the larger structure they imply. This does not mean scientific consensus exists. It does not. Many physicists prefer other interpretations or avoid committing strongly to any interpretation at all. But Everett's once dismissed proposal is now impossible to ignore in serious foundational debates. To understand why, imagine two competing instincts in science. One instinct says, keep ontology small. Do not assume giant unseen structures without necessity. If one world explains observations, why posit many? The other instinct says, keep laws simple. Do not add special collapse mechanisms or observer exceptions if the existing equations already work smoothly. Everett strongly satisfies the second instinct, while offending the first. Collapse theories satisfy the first instinct more comfortably, while introducing new mechanisms that Everett tried to avoid. That tension helps explain why the argument remains alive. There is also a psychological reason many worlds fascinates people. It takes moments of regret, chance, and uncertainty, and gives them physical weight. The road not taken is no longer only a metaphor. The life not lived becomes, in some form, another branch. You said yes somewhere else. You said no somewhere else. You stayed. You left. You met them. You never did. You survived tonight. You did not. Whether or not that picture is correct physics, it speaks directly to human imagination, because ordinary life is full of forks in the road. But Everett's original motivation was technical. He wanted to solve the measurement problem without collapse. The emotional impact came later when people realized what continuous quantum evolution might imply at large scale. Today, whenever people discuss branching realities, alternate histories grounded in physics, or the possibility that every quantum outcome continues, they are walking through a door Everett helped build. Whether that door opens onto truth or onto an elegant mistake is still unsettled. But one fact is certain. He refused collapse when many accepted it, and in doing so, he transformed a technical puzzle about measurement into one of the largest questions science can ask. If the equations never stop, how many versions of reality keep going with them? What many worlds actually means. Many people hear the words many worlds and immediately imagine a dramatic picture where brand new universes explode into existence every second, each one containing different versions of people making different choices. That image is common in movies, online discussions, and simplified explanations, but it is not the most accurate way to describe what the theory is trying to say. The central object in this discussion is the wave function. In quantum mechanics, the wave function is the mathematical description of a system and the possibilities connected to it. It contains the structure that allows predictions about what outcomes can occur and with what probabilities. In everyday explanations, people often jump straight to worlds and timelines, but the real starting point is this mathematical state, evolving through time according to quantum laws. In the standard equations, that evolution is continuous. The wave function changes smoothly and predictably according to the rules of the theory. There is no sudden break built into the core mathematics where nature must stop and pick one option in a mysterious way. The collapse idea was introduced as an interpretation of what measurements seem to show, but the equations themselves naturally describe continuous development. Many worlds asks a direct question: what if we do not add collapse at all? What if the wave function always keeps evolving under the same rules? If that is done, then when a system contains multiple possible outcomes, those outcomes remain present within the total description rather than disappearing. But this still does not mean cartoon universes splitting like balloons in the sky. What it means is that different components of the wave function become separated in such a way that they no longer influence one another in normal experience. These separated components are often called branches. A branch is not a glowing road through space. It is not a portal destination. It is a way of describing outcomes that have become effectively independent because of physical interactions with the surrounding environment. Once separated strongly enough, observers inside one branch experience one consistent result and do not experience the others. This is where a key term becomes essential: decoherence. Decoherence is one of the most important ideas for understanding modern many worlds discussions. It explains how quantum possibilities that could once interfere with one another lose that ability when a system becomes entangled with its environment. In simpler words, once a quantum event spreads information into the world around it, the different possible outcomes stop behaving like overlapping possibilities and begin behaving like separate alternatives. Think about how difficult it is to isolate anything in the real world. Even a small object is constantly hit by air molecules, light photons, thermal vibrations, and surrounding particles. Dust touches surfaces. Heat moves through materials. Light reflects off objects into the room. Every one of these interactions can carry information away. At microscopic scales, that matters enormously. Suppose a particle can follow two possible paths. If perfectly isolated, those paths may interfere and create measurable quantum effects. But if the particle interacts with the environment, tiny traces of path information leak outward. Air molecules bounce differently. Photons scatter differently. The environment becomes correlated with the outcome. Once that happens on a large enough scale, interference becomes effectively lost. The possibilities no longer behave like one blended quantum state in practice. They act like separate outcomes. That process is what gives rise to branching language. So when people say reality splits, the more careful description is that the universal wave function evolves into components that decohere from one another. Those components no longer interact in ways that ordinary observers can notice. Each contains a consistent version of events. This may sound abstract, so concrete examples help. Take a coin toss. At everyday scale, a coin toss seems classical. You flip the coin, it spins, lands, and shows heads or tails. But the detailed motion of the coin depends on countless microscopic conditions. Exact finger pressure, tiny air currents, surface texture, molecular motion, vibrations in the table, and more. In principle, some of those factors trace back to quantum-level events. Many worlds does not claim a magical branch appears because coins are mystical objects. It says that when quantum uncertainty is amplified into different macroscopic outcomes, the total state can contain components corresponding to heads and tails. From inside one branch, you simply see heads. In another branch, an observer correlated with that outcome sees tails. Neither observer experiences both. Each sees one ordinary result and feels they live in one normal world. Now consider a cleaner quantum example: electron spin. An electron measured along a chosen direction may be found spin up or spin down. Before measurement, the quantum description can include both possibilities. If no collapse is added, then measurement links the apparatus and observer to both possible outcomes in different branches. In one branch, the detector records spin up and the observer reads spin up. In another branch, the detector records spin down and the observer reads spin down. Again, this does not feel strange from inside the branch. Each observer sees one definite result. The weirdness appears only when considering the full mathematical description containing both correlated outcomes. This is why many worlds can sound bizarre, while everyday life remains ordinary. At the local level, each branch contains stable, familiar experiences. Tables remain tables, roads remain roads, memory remains coherent. You are not watching ghost versions of events around you. You experience one history. Now we need to correct another common misunderstanding involving human decisions. People often say every decision creates a new universe. You chose coffee instead of tea, so two worlds split. You turned left instead of right, so timelines multiplied. This language is catchy but misleading. Human decisions are mostly large-scale brain and body processes involving neurons, chemistry, stored memory, habits, emotions, and environmental inputs. These are not usually treated as dramatic branch generators by themselves, in the simplistic way popular culture suggests. What matters physically is not the romantic idea of choice, but whether quantum uncertainty becomes amplified into different macroscopic outcomes. Human brains are warm, noisy biological systems operating at classical-looking scales in many respects. That does not mean quantum physics is irrelevant to matter, because everything is made of quantum matter. But it does mean you should be cautious about imagining every ordinary thought as a clean branching event. A better way to say it is this: if quantum-level differences become amplified into different large outcomes involving brains, bodies, and environments, then those outcomes may belong to different branches in an Everett-style picture. But the branching is rooted in physical processes, not in some mystical power of personal choice. This distinction matters because it keeps the theory scientific rather than turning it into self-help mythology. Now return to decoherence, because it is the engine that makes branching meaningful. Imagine trying to keep a quantum system isolated in a laboratory. Scientists use vacuum chambers, cooling systems, shielding, and carefully controlled equipment because the environment destroys delicate quantum coherence very quickly. Even a stray photon can matter. A dust particle drifting through the setup can matter. A tiny vibration can matter. This shows how aggressive the environment is in forcing systems toward classical-looking behavior. Dust particles are constantly moving and colliding. Air molecules strike surfaces in huge numbers every second. Light photons bounce off nearly everything visible around you. These interactions spread information through the environment. Once that information is distributed, the different outcomes cease to interfere in any practical sense. That is why you do not see a cup on your desk existing as a visible blur of multiple positions. The cup is massively entangled with its surroundings. Decoherence happens extremely fast for large objects. The world looks definite because environmental interaction continuously suppresses the kind of quantum interference associated with obvious superpositions. Many worlds uses this fact not to deny everyday experience, but to explain why everyday experience is branch-specific. Large systems rapidly decohere into stable outcome patterns. Each branch contains objects in definite-looking states because interference between branches has become negligible. So when someone asks where the other branches are, the answer is not that they are hidden behind a wall in outer space. They are other effectively separate components of the total quantum state, no longer interacting with the branch you occupy in any ordinary, detectable way. This also explains why communication between branches is not part of normal physics. Once decoherence has strongly separated outcomes, rebuilding interference across complex macroscopic branches would be unimaginably difficult. In practice, each branch proceeds as if the others are inaccessible. Another misunderstanding is that branching means everything imaginable happens. That is false. Physics still constrains outcomes. Branches correspond to possibilities allowed by the quantum structure and actual interactions, not fantasy scenes with no physical basis. You do not get a branch where gravity reverses for no reason, or where mathematics stops working. The theory preserves laws. It multiplies allowed outcomes, not nonsense. The universal wave function, another phrase often used here, simply means applying quantum description to the universe as a whole, rather than treating some outside observer as separate from it. If everything physical is part of one total system, then in principle there is one evolving quantum state describing all interacting parts together. Branches are then structures within that total state. This is conceptually powerful because it removes the need for a special external measurer. Detectors, people, planets and stars are all internal parts of the same evolving physical reality. Measurements become interactions within the universe rather than magical acts imposed from outside. Does a version of you die every day? Human life feels stable because most days pass without disaster, but stability often hides how many risks are constantly present in ordinary living. Every person moves through environments filled with probabilities, many of them small enough to ignore individually, yet real enough to matter across time and population scale. You breathe air that may carry infection. You travel in vehicles surrounded by moving machines controlled by attention, reaction time, road conditions, and chance timing. You walk on stairs, wet floors, crowded streets, uneven ground, and surfaces where one slip can become serious. Inside the body, blood vessels weaken silently, heart rhythms can shift unexpectedly, cells divide with rare errors, and hidden conditions may exist long before symptoms appear. Weather adds to it through storms, flooding, lightning, falling objects, reduced visibility, and sudden changes that alter otherwise normal routines. Most of these risks are low probability in any single moment, which is why daily life usually continues without event. But low probability is not zero probability, and when multiplied across billions of people and countless moments, deadly outcomes become statistically inevitable somewhere, every day, every hour, every minute. This matters because many people imagine danger only as dramatic events, yet real probability often works through accumulation. A rare medical emergency may be uncommon for one person on one day, but common somewhere in a city full of millions. A driving incident may be unlikely during one trip, yet unavoidable across enough trips worldwide. A random fall may sound trivial until population size turns tiny odds into regular occurrences. That is how statistics behaves in real life. Individual comfort and population reality are not the same thing. You may pass through thousands of safe days, while similar people elsewhere experience the rare branch of events where timing, biology, and environment align badly. If an Everett-style many worlds picture were true, then these ordinary probabilities would carry a different interpretation. Instead of one outcome happening while others vanish completely, physically allowed outcomes linked to quantum uncertainty could continue in separate branches once amplified into large-scale events. In that framework, there may be branches where you coughed while eating dinner and choked fatally, branches where a hidden medical issue became active during sleep and you did not wake up, branches where you happened to stand in the wrong place at the wrong time during an accident, branches where a cell mutation that remained harmless here developed aggressively there, and branches where an avoided collision was not avoided. The key point is not drama, but ordinary statistical variation. Human life already contains many low probability hazards. Branching interpretations would apply to those hazards only when rooted in physical uncertainty that becomes amplified into different outcomes. Scientific precision is essential here because this subject is often distorted into fantasy. It does not mean your conscious awareness jumps away from dying branches into surviving ones. There is no accepted evidence for minds transferring between branches, no measured process showing memories hopping across realities, and no scientific basis for treating close calls as proof that consciousness escaped from another outcome. Those ideas are popular because they are emotionally powerful, not because they are supported by data. The many worlds claim, if adopted, is much narrower and more technical. It concerns mathematically separate continuations of physical states within the quantum description. It says different outcomes may persist in separate branches. It does not say a single stream of awareness teleports among them. That distinction becomes sharper when we ask the hardest question in the topic. If copies exist after branching, which one is you? Before a split, in the simplified thought experiment sense, there is one observer with one memory history. That observer remembers childhood, recent events, plans for tomorrow, and the feeling of being a single, continuing person. After branching, there would be two future observers emerging from the same prior state, each carrying identical memories up to the branch point and then diverging immediately afterward. One remembers seeing one result, the other remembers seeing another. Each would naturally claim to be the continuation of the earlier person because each contains the same past records up to the moment of separation. This creates an identity problem, but it should be framed scientifically rather than romantically. The issue is not souls or destiny. It concerns models of consciousness, memory continuity, and observer identity. If one prior brain state leads to two later brain states with shared memories, does personal continuity extend to both? Does it divide? Is the earlier identity replaced by two descendants rather than continued as one? Neuroscience does not provide a settled answer because neuroscience has not discovered a single simple object called the self that can be tracked like a serial number moving through time. Instead, the brain appears to construct the sense of self through interacting systems involving memory, body representation, attention, prediction, emotion, and narrative organization. In ordinary life, continuity feels straightforward because branching copies do not visibly occur in daily experience. You wake up with memories from yesterday and assume the same self continued into today. That assumption works practically because memory networks, bodily continuity, and environmental records all align. But in a branching thought experiment, those usual cues no longer choose a single successor. Two later observers may each satisfy many criteria normally used to define continuation. Both remember the same yesterday. Both recognize the same family. Both believe they are the same person who existed moments earlier. The question then becomes whether identity is one-to-one, one-to-many, or something our ordinary language was never designed to handle. Modern consciousness science offers no universally accepted solution because consciousness itself remains incompletely understood. Some theories focus on integrated information, some on global broadcasting of brain signals, some on predictive processing, some on higher order representation, and others on network dynamics. None of these theories cleanly resolves what should count as the same person across branching duplicates. They may explain how conscious states arise or organize, but identity across exact copying or branching remains conceptually difficult. This is why physicists and philosophers often meet at the edge of the problem, while neuroscience provides pieces rather than a final verdict. Now consider the second question, who is you, in another timeline, using that phrase only as shorthand for another branch history. Biological identity seems easier at first. You are partly defined by your genome, the inherited DNA that shaped development. You are also shaped by brain wiring built through growth and experience, by memory, continuity linking past to present, by body state including hormones, injuries, age, health, and physiology, and by constant interaction with environment, culture, language, relationships, stress, and opportunity. The person reading this today is not only genes and not only memories, but a living system formed by all of these together. If another branch version of you began from a shared earlier state, it might initially be extremely similar. But small changes compound quickly. One missed call may alter where you go that afternoon. A different breakfast may affect mood, energy, blood sugar, and later choices. A minor embarrassment may change confidence during an important conversation. A small injury scar may alter behavior, sleep, or self-image. One accepted opportunity may redirect career path, city, relationships, and skills. Tiny differences can cascade through social and biological systems because human lives are sensitive to feedback loops. Within months, branch versions could diverge in habits, friendships, stress levels, finances, and emotional patterns. Within years, they might be difficult to recognize psychologically, even if they share ancestry and early memories. One version may become disciplined through circumstances that forced adaptation. Another may become anxious after trauma. One may remain healthy, another may live with chronic pain. One may raise children, another may remain alone. One may relocate and absorb a new culture. Another may never leave home. The farther from the branch point, the weaker intuitive sameness becomes. Neuroscience supports this growing divergence because the brain is plastic. Neural connections strengthen, weaken, and reorganize through repeated experience. Memory is updated rather than stored as a fixed recording. Stress changes cognition. Sleep affects emotional regulation. Social life reshapes priorities. Injury can alter personality. Learning rewires skill networks. There is no untouched core sitting outside these processes. The self is continuously reconstructed from ongoing brain activity interacting with the world. Research into selfhood has also found no single permanent self-center hidden inside the brain. There is no solitary command chamber where an unchanging inner owner sits. Instead, self-related processing involves distributed networks handling autobiographical memory, bodily awareness, attention, emotional tagging, future simulation, and narrative coherence. The feeling of being one person arises from coordinated processes, not from one isolated object. That has important consequences for the branch question. Another branch you may share genetic origin and early memory ancestry, yet not share present identity continuity in the strong everyday sense people imagine. It may be closer to an identical twin created from the same starting template than to the current you reading this sentence. The twin comparison is not perfect because branch versions would initially share exact prior memories, but as time passes, divergence could become as deep as between relatives who grew into very different adults. This also means emotional reactions to branch versions should be handled carefully. People often imagine a hidden better self somewhere who made wiser choices, or a tragic self who suffered instead. But if divergence grows rapidly, those later individuals may no longer represent simple alternate upgrades or downgrades of the present self. They become separate biographies shaped by different pressures and learning histories. They are descendants of a shared past pattern, not magical proof that one true self was lost. Returning to the earlier question of daily death risk, the same reasoning applies. If there were branches where you did not survive certain events, those branches would contain observers only up to the point survival ended. Other branches would continue with future versions whose identities keep changing over time anyway. There is no neat immortal center guaranteed to ride the safest path. There are only different continuations if branching interpretations are correct, each shaped by ordinary biology and circumstance. The scientific lesson is less comforting and more realistic than internet myths. Human identity is already dynamic in one world. Memory shifts, bodies age, personalities adapt, goals change, and relationships rewrite who we become. Add branching thought experiments, and identity becomes even less like a solid object and more like an evolving pattern. The question, which one is the real you, may be badly formed if multiple later versions preserve legitimate continuity from the same earlier state. So does a version of you die every day? In probability terms, human populations constantly generate deadly outcomes somewhere from small risks. In a many worlds interpretation, some branches could contain those outcomes. But does that mean your awareness escapes into safer branches, preserving one's central self? Science gives no support for that claim. Does another branch version count as you in the strongest personal sense? Neuroscience gives no settled answer and may suggest that identity is already too distributed and changeable for a simple yes or no. What remains solid is this: the self you know now is built from memory continuity, body continuity, and present brain activity tied to one lived history. Whatever happens in hypothetical other branches would not replace the practical reality of the person existing here, shaped by this body, this memory stream, and this specific chain of events. The dark idea, quantum immortality. Among all the ideas connected to many worlds, none has attracted more fascination and confusion than quantum immortality. It sounds dramatic, almost like science has discovered a hidden escape from death. But that is not what mainstream physics has established. It must be introduced carefully, because it is not an accepted scientific conclusion. It is a thought experiment built from combining speculative assumptions about branching quantum outcomes with unresolved questions about consciousness and personal identity. It became widely known through discussions by physicists Max Tegmark and others, but popularity should not be mistaken for proof. The basic claim begins with a simplified reading of many worlds. If quantum outcomes do not collapse into one result, and if all allowed outcomes continue in separate branches, then there may be branches where an observer survives events that are fatal in other branches. A dangerous accident may kill in one branch while narrowly missing in another. A medical crisis may become terminal in one branch while treatable in another. A mechanical failure may end badly in one branch while resolving safely elsewhere. From that starting point, some people take a further step and argue that conscious experience would only ever continue in branches where survival occurs. This leads to the phrase quantum immortality. The claim is not that the body cannot be harmed, nor that no branches contain death. It says that from the first-person point of view, awareness would always find itself in branches where it continues, because branches where awareness ends cannot be experienced afterward. In that framing, death may happen in many branches, but the observer would never be there to notice non-existence. So subjective experience always tracks surviving continuations. This idea feels powerful because it mixes two truths with several unsupported leaps. One truth is that dead observers do not report experiences afterward. Another is that some branching interpretations discuss multiple continuations of outcomes. But the leap occurs when these facts are turned into a rule, saying consciousness must continue along survival paths. Physics has not demonstrated that rule. The first major problem is that consciousness itself has no settled definition inside physics. Quantum mechanics describes states, probabilities, measurements, and interactions. It does not contain an agreed equation for subjective awareness. Scientists study consciousness through neuroscience, cognitive science, psychology, and philosophy of mind, but no universal model tells us exactly what consciousness is, how it arises, or how it should be tracked across copies or branches. Without that foundation, claims about consciousness following one branch over another are already standing on uncertain ground. The second problem is that there is no evidence minds transfer between branches. Many worlds, if true, would describe separate continuations of correlated physical states. It does not provide a mechanism where a single mind abandons one branch and jumps into another. That popular image treats consciousness like a traveler moving between realities. There is no accepted scientific basis for such movement. In a branching picture, there would simply be different observer continuations, each tied to their own physical branch. The third problem is often ignored because it makes the idea far less appealing. Surviving branches do not have to be healthy branches. Even if one imagined that some observer continuations persist through dangerous events, those continuations might involve severe injury, chronic disability, reduced awareness, extreme pain, or medical decline. Survival is not equivalent to flourishing. The phrase immortality hides this issue because it sounds like endless normal life, rather than uncertain continuation under worsening conditions. Another major issue concerns probability measure, sometimes called branch weight. In quantum theory, outcomes are not treated as equal in every sense. Some outcomes carry much higher probability weight than others. If survival branches exist but become vanishingly rare compared with branches where death occurs, then appealing to their mere existence may miss the statistical structure of the theory. Critics argue that saying a branch exists is not enough. One must ask how much weight that branch carries and what that means for rational expectation. This creates a serious challenge. If 1 million overwhelmingly weighted branches contain death and one tiny branch contains survival, does it make sense to focus only on the tiny surviving branch as if it dominates experience? Many physicists and philosophers say no. Probability cannot simply be ignored because some continuation exists somewhere in the formal structure. That is one reason many physicists reject quantum immortality even if they take many worlds seriously. Accepting branching outcomes does not require accepting claims about guaranteed subjective survival. One can support Everett-style interpretations while rejecting the immortality argument as a misuse of them. People still find the idea disturbing for understandable reasons. The first reason is the subjective survival claim itself. It challenges the ordinary belief that death ends personal experience. Even without proof, the suggestion that awareness might always continue somewhere captures attention because it touches a universal fear. The second reason is how people reinterpret close calls. Someone narrowly avoids an accident, recovers from illness, or escapes danger by seconds, then wonders whether another branch ended differently. This near-miss interpretation turns normal probability into existential mystery. It can feel meaningful because rare escapes are emotionally intense, but emotional intensity is not scientific evidence. The third reason involves continuity questions. If many future versions exist after branching, which one counts as you? If one version survives and another does not, does survival elsewhere preserve personal identity here? These questions are unsettling because they expose how unclear our everyday concept of self becomes under duplication scenarios. Yet none of this should be mistaken for practical guidance. A strong safety clarification is necessary. Quantum immortality is not evidence that humans are immortal, invincible, protected by hidden physics, or safe to take reckless risks. It is not a reason to ignore danger, neglect health, gamble with life, or test survival. Real-world consequences in this branch of experience are real consequences. Cars injure people, illness kills people, falls disable people, fire burns people. Physics speculation does not cancel biology or risk. Even as a thought experiment, the argument depends on assumptions stacked on assumptions. It assumes some many-world-style interpretation is correct. It assumes consciousness can be meaningfully discussed across branches. It assumes personal identity maps onto certain continuations. It assumes probability measure does not block the conclusion. Each layer is disputed. When several disputed layers are combined, certainty becomes impossible. Experts often raise a simpler objection. If survival branches exist, they may have tiny measure. In practical terms, that means they could be mathematically present, but overwhelmingly unrepresentative. Rational expectation in science usually follows weighted probabilities, not mere logical possibility. You do not plan life around microscopic chances while ignoring dominant outcomes. Critics argue that quantum immortality does exactly that. There is also a hidden language problem in the term itself. Immortality usually means endless life or immunity from death. The thought experiment offers neither. At best, it speculates about continued observer states under some circumstances. Aging, injury, disease progression, cognitive decline, and eventual limits are still unresolved. Even within the speculative framework, immortality is more dramatic branding than accurate description. What the topic really reveals is not secret eternal life, but how poorly ordinary language handles branching identity questions. In a single history worldview, death is straightforward. A person's biological processes stop and conscious experience ends. In a branching thought experiment, some continuations may stop while others continue. That complicates language, but complication is not proof of immortality. The attraction of quantum immortality comes from psychology as much as physics. Humans dislike finality. We search for loopholes in mortality through religion, technology, legacy, or theory. A concept that appears scientific while offering escape from death naturally spreads fast. But wanting something to be true does not make it true. The scientifically responsible position is narrower. Quantum immortality is an interesting thought experiment about branching observers and subjective uncertainty. It is not established science. It has unresolved assumptions, weak evidential support, major conceptual problems, and broad rejection among physicists as a literal conclusion. So why discuss it at all? Because it exposes the sharp edge of many worlds' reasoning. If all outcomes continue, then uncomfortable questions follow about what observers should expect, what identity means, and how probability relates to experience. Quantum immortality is one attempt to answer those questions, but it remains deeply contested. In the end, the dark power of the idea is not that it proves death can be escaped. It is that it forces people to confront how little science currently knows about consciousness, identity, and first-person experience when placed inside strange models of reality. That uncertainty is real. The immortality claim is not. Why most physicists push back. Many worlds remains one of the most famous interpretations of quantum mechanics, but fame should not be confused with acceptance. While some respected physicists defend it, many others remain unconvinced or simply uninterested in adopting it as the best description of reality. Their resistance is not based on fear of strange ideas, because physics already contains many strange ideas that are strongly accepted when supported by evidence. The pushback comes from specific technical and conceptual objections. To many researchers, the interpretation raises major questions without clearly solving enough of them. It may remove one mystery, but in doing so, it can create several others. The first and most common objection is that many worlds offers no new testable predictions in ordinary use. In science, theories gain strength when they predict outcomes that differ from rival explanations, and those predictions can be checked by experiment. If two models always produce the same measurable results, then choosing between them becomes difficult because evidence does not strongly favour one over the other. Much of the debate around quantum interpretations exists in exactly this territory. Standard quantum mechanics, collapse-based views, pilot wave approaches, and many worlds often agree on the numerical outcomes of laboratory experiments. They may describe the meaning of those outcomes differently, but the detector clicks in the same pattern, the interference experiment gives the same statistics, and the measured probabilities match the same equations. When this happens, many working physicists ask a practical question. If the observable results are identical, why should we commit to the interpretation that adds an enormous branching structure? This does not mean untestable ideas are automatically worthless. Conceptual clarity matters, and internal consistency matters. But in a field driven by measurement, many scientists hesitate to treat interpretations as established reality when experiments do not clearly distinguish them. Some therefore see many worlds as an interesting philosophical reading of the math, rather than a confirmed description of nature. The second major objection concerns probability. This is one of the deepest challenges many worlds faces, because quantum mechanics is built around probabilities that match experiments with extraordinary precision. The Born rule gives the standard probabilities for outcomes based on the wave function. It is not a side detail. It is central to how quantum predictions succeed. In a single outcome picture, probability has an intuitive meaning. You perform a measurement, one result occurs, and probability describes how likely each possible result was before it happened. But if many worlds says all outcomes happen in some branch, then the normal meaning of probability becomes harder to explain. If every result occurs, in what sense was one result more likely than another? Supporters respond that branch weights still matter and that rational observers should expect outcomes according to those weights. Sophisticated arguments have been developed using decision theory, symmetry reasoning, and the mathematical structure of amplitudes. Critics reply that these arguments may recover useful betting behaviour, but do not fully explain why subjective uncertainty should arise when all outcomes occur. The problem becomes sharper with repeated experiments. In real laboratories, frequencies match born rule probabilities. If outcomes branch endlessly, why should observers typically find frequencies matching those exact weights rather than something else? Supporters say most observers in high-weight branches will observe the standard statistics. Critics say the interpretation still struggles to justify why probability feels real when nothing is excluded from happening somewhere. For many physicists, this is not a small issue. If a theory keeps all outcomes but cannot cleanly explain why measured probabilities take their observed form, then it has not fully accounted for one of quantum mechanics' most important facts. The third objection is known as the preferred basis problem. Many worlds talks about branches, worlds, or separate outcome histories, but what exactly counts as a branch? Nature does not come with labels attached saying, this is where one world ends and another begins. The universal quantum state can be mathematically represented in different ways, and the decomposition into branches is not always obvious. Imagine a measurement setup producing macroscopically different outcomes, such as detector left versus detector right. That sounds simple. But at the level of raw mathematics, many equivalent ways of expressing a state may exist. Why should one particular set of states be treated as the real branches rather than another abstract combination? Decoherence is often used to answer this by showing that stable classical-like states emerge through environmental interaction. Certain outcome structures become robust and effectively independent, making them natural candidates for branches. This is a strong reply, and many supporters believe it solves most of the issue. Even so, critics argue that branch boundaries remain approximate rather than fundamental. If worlds are central to the interpretation, should their definition not be cleaner? This concern matters because vague branching language can create confusion. If worlds are only approximate patterns, then statements about exact numbers of worlds or precise split moments become misleading. Some physicists are uncomfortable grounding ontology in structures that seem emergent and fuzzy rather than sharply defined. The fourth objection concerns identity. Many worlds often becomes popular through personal examples. Another, you took the other job. Another, you moved cities. Another, you survived an accident. But from a scientific perspective, copies are not obviously continued you in any simple sense. Suppose one observer state branches into two later observers with shared memories up to that point. Each future observer claims continuity with the past version, but identity does not automatically duplicate just because information duplicates. Everyday language assumes one past person leads to one future person. Branching breaks that assumption. Some scientists view this as a sign that personal narratives built around many worlds are overstated. Even if branching occurred, it does not follow that you continue as a single center of awareness spread across copies. It may instead mean two new successors exist, each related to the earlier observer but no longer identical in experience. If so, claims like, "you survive somewhere," become less clear than they first sound. This objection becomes stronger when tied to neuroscience. The brain's sense of self appears to arise from distributed processes, memory continuity, and bodily integration, rather than from a simple, indivisible entity. If identity is already constructed and dynamic, then many world stories about oneself extending across branches may be using ordinary language beyond where it remains reliable. Because of that, many physicists prefer to avoid personal identity claims entirely. They focus on equations and measurement records, rather than dramatic statements about multiple future selves. The fifth objection targets quantum immortality and similar conclusions. Some researchers explicitly argue that immortality does not follow from many worlds. Even if branching outcomes exist, it does not logically imply guaranteed subjective survival. That stronger claim requires additional assumptions about consciousness, observer weighting, and what counts as personal continuation. Critics note that branches involving death, unconsciousness, severe injury, or cognitive breakdown cannot simply be ignored. If many continuations contain non-survival or degraded states, why privilege rare survival branches as the true seat of experience? The move from "some branches survive" to "you will always experience survival" is widely viewed as unjustified. There is also a statistical objection. If survival branches become extremely low weight compared with non-survival branches, then treating them as dominant from a first-person perspective conflicts with how probabilities are normally used in science. Existence alone does not erase measure. Many researchers therefore see quantum immortality as a misuse of branching language, rather than a legitimate consequence. Beyond these 5 headline objections, there is also a broader cultural reason for skepticism. Many physicists work in areas where interpretation debates do not change practical results. They build devices, test materials, model particles, or calculate spectra without needing to decide whether worlds branch. From that perspective, spending energy on vast unseen ontologies can seem unnecessary. This practical mindset should not be mistaken for anti-intellectualism. It reflects the history of physics, where progress often came from focusing on measurable structure first and metaphysical interpretation later. If an interpretation does not guide new experiments or calculations, many researchers place it low on their priority list. Another concern is economy of explanation. Science often values simplicity, but simplicity can mean different things. Supporters of many worlds say it is simple because it keeps one equation and removes collapse. Critics say it is extravagant because it fills reality with countless branches. Both sides claim simplicity, but they measure it differently. One counts laws, the other counts ontology. This explains why debates persist for decades without resolution. Different scientists weigh virtues differently. Some prioritize mathematical continuity. Others prioritize minimal commitments about what exists. Some care most about probability foundations. Others care most about experimental distinctness. Even among critics, rejection is not always absolute. Some physicists think many worlds may contain useful insights yet remain incomplete. Others think decoherence explains much of the appearance of branching without requiring full many worlds ontology. Others remain agnostic, treating all current interpretations as provisional. What unites most pushback is not hostility to bold ideas, but demand for stronger grounding. If an interpretation asks us to accept an immense branching reality, then many scientists want clear gains in return. Sharper probability foundations, cleaner definitions, or testable consequences. Without those gains, skepticism remains reasonable. This is important because public discussions often frame the issue badly. They present many worlds as if physicists reject it because it sounds weird. That is false. Physics accepts black holes, curved space-time, wave-particle duality, and quantum tunneling because evidence supports them strongly. Weirdness alone is not a barrier. Weak explanatory advantage, unresolved technical issues, and lack of distinct tests are the real barriers. Many worlds is mathematically connected to accepted quantum theory, yet interpretationally unsettled. It removes collapse, yet inherits probability and identity puzzles. It offers conceptual unity, yet demands ontological scale many find excessive. If rival interpretations gain stronger footing, or experiments favour modifications of standard quantum theory, support could shrink. At present, many physicists remain unconvinced not because they fear new realities, but because they think the current case is incomplete. The experiments that made many worlds hard to ignore. The debate around many worlds is often described in terms of interpretation, but it did not arise in isolation from real laboratory science. It is closely tied to a series of experiments that forced physicists to accept that the microscopic world behaves in ways that do not match classical intuition. These experiments did not prove any single interpretation, including many worlds. But they made it increasingly difficult to ignore the idea that quantum behavior is fundamentally different from everyday physical experience. Each experiment added pressure on old assumptions, showing that particles, measurement, and information do not behave in simple, linear ways. The most famous starting point is the double-slit experiment, which has become one of the central demonstrations of quantum mechanics. In this setup, particles such as electrons or photons are sent toward a barrier with two narrow openings. Behind the barrier is a detection screen that records where the particles land. If you expect classical behavior, you would assume each particle passes through one slit or the other, and forms two simple clusters on the screen. Instead, what appears is a pattern of interference, similar to waves overlapping in water. This suggests that each particle behaves in a way that spreads across both paths and interacts with itself in a wave-like manner. The surprising part becomes even clearer when particles are sent one at a time. Even without multiple particles interfering with each other, the interference pattern still builds up over time. This means each individual particle seems to pass through a state where both paths matter in producing the final result. When no measurement is made to determine which slit the particle goes through, the wave-like pattern appears. When a measurement is introduced to determine the path, the interference disappears and the pattern becomes particle-like. This shift is not caused by changes in the particles themselves, but by the presence or absence of path information, which suggests that observation or interaction plays a crucial role in determining the outcome. This experiment is often summarized as particles interfering with themselves, but the deeper implication is that the classical idea of a single, well-defined path is not sufficient at quantum scales. Instead, the system behaves as if multiple possibilities contribute to the outcome until interaction forces a definite record. This is one of the reasons many worlds gained attention, because it offers a way of describing these multiple contributing possibilities as real components of a single evolving quantum state, rather than as unrealized alternatives that vanish upon observation. The next major development came from a different direction, involving work by physicist John Bell. Bell addressed a fundamental question about whether quantum mechanics could be explained by hidden variables, meaning underlying factors that determine outcomes in a deterministic way, even if they are not directly observed. He developed mathematical inequalities that could be tested experimentally. If those inequalities were violated, it would mean that no local hidden variable theory could fully explain quantum behavior. Experiments inspired by Bell's work were performed over several decades, and they consistently showed violations of Bell inequalities. These results indicated that reality does not behave in a way compatible with simple, local, hidden, variable explanations. In practical terms, this means that the correlations observed between entangled particles cannot be explained by classical ideas, where each particle carries pre-existing instructions about how to behave and only interacts with nearby influences. Instead, the results show non-classical correlations that suggest quantum systems are deeply interconnected in ways that defy classical separation. This is often summarized by saying that reality is non-classical, but that phrase hides the depth of what is actually observed. Entangled particles behave in ways that cannot be reproduced by any model that assumes independent local properties assigned in advance. When measurements are performed, the results are correlated in precise statistical patterns predicted by quantum mechanics and confirmed in experiments. These correlations appear even when the particles are separated by large distances, which challenges classical intuitions about locality and independence. Bell test experiments do not prove many worlds, but they strongly support the idea that quantum systems cannot be fully described using classical hidden variables that assign fixed outcomes before measurement. This strengthens the position of quantum theory as a fundamentally different framework from classical physics, and it forces interpretations to account for these non-classical correlations in some way. Many worlds responds by treating the quantum state as fully real and evolving without collapse, allowing correlations to be explained through branching structure rather than hidden preset values. Another set of experiments that deepen the conceptual challenge comes from delayed choice experiments. These experiments explore what happens when the decision about how to measure a quantum system is made after the system has already entered the experimental setup. In some versions, a particle passes through an interferometer where it could take multiple paths, and the experimental arrangement determining whether path information is observed can be changed even after the particle has already entered the system. The results show that the type of measurement chosen affects the outcome pattern, even when that choice is made at a time that seems to come after the particle has already made its journey through the apparatus. This does not mean the past is being rewritten in a literal sense, but it does show that quantum events cannot be understood in simple terms of fixed trajectories independent of measurement context. Instead, the experimental setup as a whole, including later choices, plays a role in defining what can be said about the system. Delayed choice experiments challenge the idea that particles carry definite histories in the classical sense. Instead, the quantum description depends on the full experimental arrangement, including how and when information is obtained. This reinforces the view that quantum systems are not simply objects following predetermined paths, but are described by a structure that only becomes definite relative to measurement conditions. While these experiments are often discussed in terms of foundational questions, they also connect directly to modern technology through quantum computing. Quantum computers use principles such as superposition and interference to perform calculations in ways that classical computers cannot easily replicate. Instead of storing information in simple binary states alone, quantum systems can represent combinations of states and process them through controlled interference effects. Companies such as IBM and Google have built experimental quantum processors that demonstrate these principles in practice. In these systems, qubits can exist in superpositions of states and interact in ways that produce computational results dependent on interference patterns. Algorithms designed for quantum computers take advantage of these properties to explore computational spaces that would be extremely difficult for classical machines to simulate directly. The operational success of quantum computing has made the underlying physics feel less abstract. When interference and superposition are used to perform real calculations, they are no longer just philosophical curiosities. They become practical tools. This has revived public and scientific interest in interpretations like many worlds, because one intuitive way to think about quantum computation is that multiple computational paths are explored simultaneously within the quantum state. However, it is important to clarify a common misunderstanding. Quantum computers do not prove many worlds. They function based on quantum mechanics, but the success of quantum computation does not require adopting any specific interpretation of what quantum mechanics means. Whether one views superposition as real branching worlds, as a mathematical tool, or as a probability structure, the predictions of quantum computing remain the same. The machines work regardless of interpretational stance. What quantum computing does is make the underlying behavior of quantum systems more tangible. It shows that superposition and interference are not just theoretical ideas, but operational resources that can be engineered and controlled. This practical reality has made it harder for interpretations of quantum mechanics to remain purely philosophical discussions detached from experiment, because the same principles involved in interpretational debates are now being used in functional technologies. Taken together, these experiments form a consistent pattern. The double-slit experiment shows that particles behave in wave-like ways when not measured for path information. Bell test experiments show that reality does not fit classical hidden variable explanations. Delayed choice experiments show that measurement context affects what can be meaningfully said about quantum history. And quantum computing demonstrates that superposition and interference are real operational features of nature. None of these results uniquely confirms many worlds, but they collectively establish that quantum behavior cannot be reduced to simple classical pictures. This is what makes many worlds difficult to dismiss entirely. It is not required by the data, but it is also not disconnected from it. It sits as one possible way of organizing the strange but experimentally verified structure revealed by these experiments, where outcomes, correlations, and information do not behave in ways that match everyday intuition. Alternative interpretations of quantum theory. Quantum mechanics does not come with a single agreed meaning attached to it. The mathematical structure is extremely successful at predicting experimental results, but what that structure says about reality itself has been interpreted in different ways by physicists over time. These interpretations do not usually change the predictions of standard experiments, which is why the debate continues even after decades of research. Instead, they offer different explanations of what is happening underneath the equations, especially when it comes to measurement, probability, and the nature of physical reality. Many worlds is one of these interpretations, but it is important to understand that it is not the only one, and it is not the dominant consensus view among physicists. One of the oldest and most widely taught interpretations is the Copenhagen interpretation. In this view, quantum systems are described by mathematical objects that represent probabilities of different outcomes, and when a measurement is performed, the system yields one definite result. Before measurement, the system is not treated as having a single fixed outcome in the classical sense, but after measurement, only one outcome is observed. The transition from multiple possibilities to one observed result is often described as collapse of the wave function. In this framework, collapse is not necessarily explained in detail as a physical process, but is treated as part of how measurement works in practice. The key idea is that quantum mechanics provides probabilities for outcomes, and measurement produces one of those outcomes without requiring additional parallel realities. This interpretation avoids the need for branching worlds entirely by treating the wave function as a tool for predicting observations rather than a literal description of multiple coexisting outcomes. Another major alternative is pilot wave theory, also known as Bohmian mechanics. In this approach, particles are always assumed to have definite positions and trajectories, even when not observed. Their motion is guided by a wave function, which evolves according to quantum rules. But unlike many worlds, the wave function does not represent multiple real outcomes. Instead, it acts as a guiding field that influences particle motion in a deterministic way. The randomness observed in quantum experiments arises not from multiple branching outcomes, but from our lack of knowledge about initial conditions. In this interpretation, there are no splitting selves or parallel histories. There is a single actual configuration of particles moving through space, guided by a non-classical wave. This allows the theory to preserve determinism at a deeper level, while still reproducing standard quantum predictions. A different family of ideas is represented by objective collapse models. These theories modify quantum mechanics itself by introducing a real physical process that causes wave functions to collapse spontaneously. In standard quantum theory, collapse is often treated as an addition tied to measurement, but in objective collapse models, collapse is an actual physical mechanism that happens regardless of observation. It occurs randomly or under certain conditions, such as when systems become large or complex enough. This means that quantum superpositions do not persist indefinitely at macroscopic scales because they are actively destroyed by physical collapse events. These models attempt to solve the measurement problem by making collapse part of nature itself rather than an interpretational add-on. In this view, There is no need for branching universes because only one outcome becomes physically real through collapse. Another important perspective is relational quantum mechanics, which takes a different approach to the idea of quantum states altogether. In this interpretation, the state of a system is not absolute, but depends on the relationship between the system and the observer or interacting system. This means that different observers can have different valid descriptions of the same quantum event, depending on their interactions with it. There is no single global state that exists independently of all observers. Instead, reality is described in terms of interactions and relations between systems. Measurement outcomes are not absolute events in a universal sense, but are relative to the observer who interacts with the system. This removes the need for a universal collapse or branching structure, because quantum states are not treated as global entities that must resolve into a single outcome for everyone at once. Each of these interpretations tries to address the same underlying experimental facts, but they do so in very different ways. The Copenhagen interpretation introduces a boundary between quantum and classical measurement outcomes. Pilot wave theory introduces hidden deterministic motion guided by a wave. Objective collapse models modify the physics itself to enforce definite outcomes. Relational interpretations change the meaning of quantum states depending on the observer. Many worlds instead removes collapse entirely and treats all outcomes as part of a continuously evolving quantum structure. Now, if another you dies tonight, what would you notice? If another you dies tonight, what would you notice? From a strict scientific standpoint, the most direct answer is that you would probably notice nothing at all. This is a consequence of how quantum descriptions of physical systems behave when applied to observers who are part of those systems. If branching interpretations like many worlds are considered, then different outcomes may exist in separate, decohered branches. But each branch contains its own internally consistent observer with their own continuous memory stream. Once decoherence has separated these outcomes, the branches no longer interact in any meaningful physical way, which means there is no transfer of information, no cross-branch signaling, and no mechanism by which one version of an observer could become aware of what happens in another branch. This leads to a very specific and often misunderstood consequence. Your conscious experience is always local to the branch in which your brain state continues. Consciousness, as far as neuroscience and physics currently describe it, is tied to physical processes occurring within a particular brain, shaped by its ongoing interactions with the environment. That means your memory, perception, and awareness are continuously updated by signals within your own physical pathway through time. If other branches exist where different outcomes occur, those branches contain their own independent continuations of similar brain processes, but they are not connected in a way that allows shared awareness or exchanged experience. In practical terms, this means that even if there were a branch in which a fatal event occurred, there would be no experience of that branch from the perspective of the observer who continues in another branch. The key reason is decoherence, which ensures that once macroscopic differences in outcomes arise and become entangled with the environment, the different branches stop interfering with one another. Information about one outcome becomes dispersed into countless environmental degrees of freedom, such as scattered photons, air molecule collisions, thermal vibrations, and other interactions that rapidly spread the record of what happened in a way that cannot be recombined in any realistic physical process. Once that spread occurs, each branch evolves independently, and no physical pathway remains that could transmit awareness between them. Because of this, there is no mechanism for receiving signals, memories, or impressions from versions of yourself in other branches. If a version of you in another branch experienced a different outcome, that version's history remains entirely contained within its own decohered physical trajectory. There is no shared communication channel, no delayed awareness, and no overlap in subjective experience. Each branch is effectively self-contained from the perspective of observers within it. This is why, in the scientific framing, You would not notice if another version of you ceased to continue in a different branch. Your memory remains strictly tied to the physical continuity of your own brain state. The neural structures that encode your experiences do not access information from other branches, because those branches are no longer physically coupled in any way that preserves coherence. Your conscious stream therefore follows a single, uninterrupted history, even if the global quantum description contains multiple non-interacting continuations. This also explains why people never report receiving information from alternate outcomes that did not occur in their experience. There is no experimental evidence of cross-branch communication, no verified cases of memory transfer between mutually exclusive outcomes, and no observed physical mechanism that would allow such exchange. From the perspective of physics, once decoherence has taken place, each branch behaves like a separate classical-like world for all practical observational purposes, even if it remains part of a larger quantum description. Despite this, many people interpret unusual life experiences in ways that seem to suggest something like branch awareness. A common pattern in online discussions involves statements such as, "I should have died but didn't," or "something about reality feels like it changed overnight." These statements often arise from emotionally intense or statistically unlikely events, such as narrowly avoiding accidents, recovering from severe illness, or experiencing sequences of coincidences that feel too structured to be random. While these experiences feel significant, they do not provide scientific evidence for timeline switching or awareness of alternate outcomes. One major factor behind these interpretations is how human memory works under stress. Memory is not a perfect recording system, but a reconstructive process that can be influenced by emotional intensity, expectation, and later reflection. When a person experiences a high-stress event, the brain prioritizes survival-relevant processing over precise encoding of every detail. Later recollection of the event may be influenced by reconstruction rather than exact replay, which can introduce distortions or strengthen certain narrative elements over others. This can create the impression that reality has shifted, when in fact memory reconstruction is adjusting how the event is recalled. Another factor is probability bias, where humans naturally underestimate how often rare events occur in large populations. When something unlikely happens to one person, it feels extraordinary. But across millions of people and billions of daily events, unlikely outcomes occur constantly. Surviving a dangerous situation can feel like a break in normal reality. But statistically, it may be expected somewhere in the population distribution at all times. Because individuals only experience their own local perspective, they tend to overinterpret rare outcomes as signs of deeper structural changes in reality. Narrative reconstruction also plays a major role. The human brain is strongly oriented toward forming coherent stories out of events, especially when those events are emotionally charged or difficult to process. After an unusual experience, the mind often organizes memories into a structured narrative that emphasizes meaning, contrast, or perceived turning points. This can lead to retrospective interpretations that make the event seem more significant or unusual than it appeared in real time. In some cases, people may reinterpret ordinary probability outcomes as evidence of reality shifting, even though no measurable physical change in external conditions has occurred. A related phenomenon often discussed in this context is the Mandela effect, where large groups of people remember historical or cultural details differently from recorded reality. Examples often involve misremembered logos, movie lines, or event details. While these cases are frequently presented in online discussions as potential evidence of alternate timelines or shifted realities, scientific explanations point to cognitive processes rather than physical changes in history. Human memory is highly susceptible to suggestion, social reinforcement, and pattern completion errors, especially when multiple people reinforce the same incorrect recollection over time. Memory errors can spread socially because people influence each other's recollections, especially in environments where discussions reinforce similar misunderstandings. Once a particular version of a memory becomes widely shared, it can feel more correct simply due to repetition, even if it differs from original records. Stress and emotional engagement can also strengthen confidence in inaccurate memories, making them feel more real than they are. These processes do not require any change in physical reality or any form of timeline alteration to explain the effect. Perception under stress can also distort how events are experienced in the moment. During high adrenaline situations, attention narrows and perception of time can change subjectively. This can lead to feelings that events unfolded unusually or that outcomes were narrowly avoided in ways that feel almost externally guided. However, these effects are well documented in neuroscience and are linked to changes in attention, memory encoding, and sensory processing during heightened emotional states. None of these phenomena provide evidence for branching awareness or movement between alternate outcomes. Chaos theory, non-quantum timelines. Chaos theory deals with systems that follow normal classical physics but behave in ways that become extremely sensitive to initial conditions. Unlike quantum mechanics, it does not require particles to exist in multiple states at once or invoke branching universes. Instead, it focuses on how small differences in starting conditions can grow over time, in systems that are deterministic but practically unpredictable. The central idea is often summarized through the butterfly effect, where a tiny change in an early condition can lead to a very large difference in later outcomes, not because reality splits, but because complex systems amplify small variations through repeated interactions. In everyday life, this can be understood through simple sequences of events that depend on timing, environment, and human action. A missed bus may not seem important in isolation, but if that bus determines whether you meet a specific person, arrive at a different location, or experience a different sequence of interactions, then the entire chain of events that follows can diverge significantly from what would have happened otherwise. A single delayed moment can shift the conditions under which future decisions are made, which then cascade into different outcomes over weeks, months, or years. In another example, one email sent at a specific time might reach a recipient before or after a critical decision point, influencing career opportunities, job assignments, or professional relationships in ways that are entirely consistent with normal causality, but highly sensitive to timing. Weather systems provide another clear illustration of chaotic behavior. A small change in atmospheric conditions, such as a slight variation in temperature, pressure, or wind direction, can determine whether a storm forms or dissipates, whether rain occurs at a particular moment, or whether a region experiences calm conditions instead of severe weather. A rain delay, for instance, might prevent a sequence of events that would otherwise have occurred, such as a traffic pattern leading to an accident or a scheduled activity taking place in unsafe conditions. These outcomes are not the result of multiple realities existing at once, but of a single evolving system in which small initial differences grow into large observable divergences. The key scientific distinction is that chaos theory does not imply parallel universes or multiple coexisting versions of reality. It operates entirely within a single universe governed by classical physics, where the laws of motion remain fixed and deterministic, but the outcomes become extremely difficult to predict due to sensitivity to initial conditions. This means that while only one actual sequence of events occurs, the space of possible outcomes is extremely wide, and small perturbations determine which path is realized. This leads to an important conceptual point that is often misunderstood. Even without invoking quantum branching or multiple universes, reality contains an enormous number of potential histories that are continuously being avoided or not realized. Every decision, every delay, every minor environmental fluctuation excludes a vast number of alternative futures that could have occurred under slightly different conditions. These unrealized paths are not physically existing alternate versions of reality, but they represent mathematically possible outcomes that were never selected by the unfolding dynamics of the system. From this perspective, chaos theory highlights how fragile long-term prediction is in complex systems. Even if the underlying rules are deterministic, the practical ability to forecast exact outcomes breaks down, because initial conditions cannot be measured with infinite precision. As time progresses, uncertainty grows, and systems that began with nearly identical conditions can evolve into vastly different states. This is why long-term weather forecasting, for example, becomes unreliable beyond certain timescales, even though the equations governing atmospheric motion are well understood. In cosmology, the term multiverse appears in several theoretical contexts, but it does not refer to a single, unified concept. Instead, it arises from different models that attempt to extend our understanding of the universe beyond the observable region. One of the most discussed frameworks is inflationary cosmology, which describes the early expansion of the universe as an extremely rapid growth phase driven by a high-energy field. In some versions of this model, inflation does not end everywhere at once. Instead, it may continue in different regions of space, producing what are often described as bubble universes. Each bubble would form its own region of space-time, potentially expanding independently with its own physical properties. These bubble universes, if they exist, would be causally disconnected from one another due to the rapid expansion of space between them. This means that even if multiple universes exist in an inflationary multiverse, they would not interact or communicate in any observable way. Each bubble would evolve according to its own initial conditions and physical laws, which may or may not resemble those of our own universe. The important point is that such models do not imply the existence of alternate versions of individual people or lives. They describe separate regions of space-time that may have entirely different large-scale properties. Another theoretical framework arises from string theory, particularly the idea known as the string landscape. In this context, the fundamental equations of string theory allow for a vast number of possible vacuum states, each corresponding to different ways that extra dimensions and fundamental fields might be configured. Each vacuum state could, in principle, give rise to a universe with different physical constants, particle types, or force strengths. This leads to the possibility of a large ensemble of universes, each occupying a different point in the landscape of possible physical laws. However, even within this framework, there is no requirement that these universes contain versions of familiar structures, such as stars, planets, or life. Many of the possible vacuum states could produce universes that are completely unrecognizable compared to our own, lacking stable atoms, chemistry, or long-lived structures necessary for complexity. Some may expand too quickly for structure to form, while others may collapse or remain in highly unstable configurations. This means that the multiverse in this context is primarily a statement about variation in physical laws, rather than a collection of parallel histories of the same life or identity. A crucial clarification is that none of these cosmological multiverse ideas necessarily imply alternate personal timelines in which individual lives are duplicated or diverged versions of the same person exist across different universes. Inflationary bubbles and string landscape vacua, if real, are fundamentally about differences in physical constants, space-time structure, and large-scale cosmic evolution, rather than variations of individual biographies. They describe universes that may differ so drastically from our own that the conditions for life, consciousness, or even stable matter might not exist at all. This is an important separation because popular discussions often merge distinct scientific ideas into a single narrative of parallel selves and alternative personal realities. In actual cosmology, multiverse hypotheses are grounded in attempts to extend physical theory to explain observed features of our universe, such as its large-scale uniformity or the values of fundamental constants. They are not designed to account for individual-level branching of human experience or to suggest that every possible life path is physically realized somewhere. current science has no confirmed way to detect other timelines or branches. Quantum mechanics predicts experiments extremely well, but different interpretations of the same equations give the same measurable results. That means whether someone believes in collapse, many worlds, or other frameworks, lab outcomes like interference patterns and entanglement statistics do not change in any detectable way. Because of this, no experiment has ever shown direct evidence of separate accessible outcomes outside the one observed result. Some theoretical ideas suggest possible indirect hints. Physicists study how quantum systems lose coherence through interaction with the environment, and this helps explain why quantum effects disappear at large scales. In extremely controlled setups, researchers can keep systems coherent longer to observe quantum behavior more clearly. But once decoherence happens, different outcomes no longer interfere and cannot exchange information. There is no known physical method to reconnect or read across these separated outcomes after that point. Cosmology and quantum gravity also explore speculative ideas about deeper structure of reality. But none of these approaches currently provide testable evidence for detectable branches or parallel timelines. Even physicists who take many worlds seriously, like Sean Carroll, treat it as an interpretation of quantum mechanics, rather than a confirmed physical discovery that can be observed directly. What science clearly knows is that quantum mechanics works, but what measurement truly means is still unresolved. Many worlds is mathematically consistent, but not experimentally proven as literal parallel universes. At the same time, there is no confirmed evidence for any mechanism that allows communication between different outcomes or histories. In normal physics, multiple possible futures can still be described using probability. Small changes in conditions can lead to different outcomes, such as accidents occurring or being avoided, but only one outcome actually happens in experience. These alternatives are not separate real timelines, just different possible results of the same physical situation. Human thought naturally imagines alternatives through counterfactual thinking, where the brain simulates what-if scenarios to understand risk and decisions. This is a cognitive process, not evidence of other realities. So the scientific position is simple. Many possible outcomes can be modelled, but only one is ever observed, and there is no verified way to detect or access other outcomes beyond the single, continuous experience tied to one physical history.